Good day, everyone. I'm Doris, okay? I will be taking you through a presentation titled Biofuels with Tailored Properties for Hybrid and Plug-in Electric Vehicles. Today's fuels do not allow engines to operate at their peak efficiency. Therefore, for the past 5 years, the Department of Energy, through Co-Optima program, has been looking into designing biomass-derived blend stock with fuel properties that boost engine efficiency. The intention is to exploit the unique properties available from biomass-derived molecules in order to produce higher value blend stock. One of such property that can be tailored to improve engine efficiency is the research octane number. This initiative aims at enabling technology for fuel engine co-optimization. From the past analysis, we have quantified various benefits associated with introducing co-optimized fuels and engines for light-duty vehicles, focusing on spark ignition engine. One of the core assumptions in the analysis was that the engine efficiency gain will be the same for vehicles with spark ignition engine and hybridized powertrain using fuel with properties tailored for spark ignition engine. However, in this present analysis, we focus more on the hybrid and plug-in hybrid vehicles by examining the opportunities to reduce the environmental effect of light-duty transportation when the fuel properties are tailored to the unique need of hybrid and plug-in hybrid vehicles in order to improve their engine efficiency. Our core parameters are incremental vehicle cost and efficiency gains. By looking at trade-off between these two parameters, we want to see the effects on the adoption of co-optimized vehicles with hybridized powertrain. The modeling suite that we use for our scenario analysis is described as follows. In this figure, ADOPT projects the changes in the light-duty vehicle composition over time as new technology enters the market. It then communicates the corresponding fuel demand to BSM, which then evaluates the cost of biofuels and the availability based on the feedstock and biorefinery availability and growth. The BSM communicates the volume of fuel consumed by time into bioeconomy age, which based on the life cycle GHG emission, water consumption, and emission factor from grid, then calculates the key energy and environmental effects over time and compare them to the business as usual case. I will take us through some of the parameters and assumptions that we use in ADOPT and the summary of our results. The temporal boundary of our analysis is between 2019 and 2050, and it covers the entire light-duty sector. We assume that vehicles with co-optimized engine is introduced in 2027, and the efficiency improvement for co-optimized conventional, which are non-hybridized vehicles, is held at 8% above the business as usual internal combustion engines vehicles. We however consider 3 scenarios for hybridized co-optimal engine with efficiency increased from 8% to 12%, and 4 different increment cost increase ranging from $100 to $1,000 with total 12 scenarios simulated in ADOPT as shown in this figure. We look at impact of the price and efficiency on the future vehicle sales. From this figure, we see that as we go from the left to the right and from top to down, we see that the vehicle sale is relatively insensitive to incremental vehicle purchase cost up to $250. However, with incremental cost about $500, there is a notable drop in the vehicle sale despite expected fuel cost saving. Also, when we move from the left to the right, we see that the effect of engine efficiency gain from 8 to 12% was less pronounced. But one significant thing to be noted on this figure is that as efficiency gains increases from 8% to 12%, we see that the share of hybrid electric vehicles increases. And therefore, we will focus on 3 major scenarios from these 12 scenarios. The first scenario, which is the best case scenario, is the case where we have $100 vehicle price increase and 12% engine efficiency. The mid-case scenario is the case where we have $500 vehicle price increase with 10% engine efficiency increase. And the conservative case will be the case when the vehicle price increase is capped at $1,000 with 8% engine efficiency. Based on the projected vehicle sales and energy consumption from HADOPT and BSM, Bioeconomy analyzed the life cycle and environmental impacts of co-deploying biofuels with hybridized powertrain. We analyzed these impacts from 2019 to 2050 using metrics such as greenhouse gas emission and water consumption. Some of the results from the bioeconomy modeling is as shown on this figure. This figure shows the life cycle GHG emission impacts within the three major cases from HADOPT and the business as usual case. The blue line on the figure represents the emission from the business as usual case. And when we look at this figure, we see that from 2019 to 2029, in the case of the business as usual scenario, we see that the GHG emissions start to decline in 2029 up until 2050 in this case. But when we look at the other three cases, with co-optimized vehicles introduced in 2027, we see that the reduction and the impact on the GHG benefit is only start to reflect after 2030 and continue to decline until 2050, leading to 17.5% reduction in the GHG emission in the best case scenario in 2050 compared to the BAU case. For the mid and conservative case, the percentage emission reduction is lower, with approximately cumulative effect of 2.4 and 2.3% in for the mid case and for the conservative case. In these two cases, the adoption of co-optimized vehicle is not as significant as the best case scenario due to higher vehicle incremental costs when we compare the cost to the best case scenario. And that is why we see a lower reduction in the GHG emission. With this in mind, we look more closer into what drives the reduction we saw, focusing on the best case scenario. We analyze the emission benefits based on different vehicle types and their impact on the emission reduction as shown in this figure. The 17.5% emission benefit we saw in 2050 from the previous figure translates to 229 million metric tons of GHG emission benefits. The major driver being the replacement of other fleets, including electric vehicles with more efficient co-optimized vehicles. We see that the major contribution is coming from the co-optimized gasoline ICEV with 46.5% emission reduction from this vehicle category, as this vehicle gain markets penetration and displaces their conventional counterparts. Another driver to the contribution is the reduced life cycle carbon intensity of co-optimal fuel and increased efficiency from biofuel co-optimized engine. Another major contribution is coming from the co-optimized hybrid electric vehicles, as the co-optimized hybrid electric vehicles displaces the conventional counterparts. We also take a deeper look into the driver behind the emission reduction. We analyze the annual mileage of each vehicle type and the corresponding emission. When we look at the gasoline internal combustion engine vehicles, we compare the cases between the business as usual and the best case. And we see from the figure on the left, we see 7.5% reduction in the vehicle mile travel between the BAU and the best case in 2050, which from the figure on the right translates to 14.3% reduction in the ICEV GHG emission in 2050 compared to BAU, with a consumer moving away from conventional ICEV and adopting co-optimized conventional ICEV. We see this leading to emission reduction. We also analyze the effect on the hybrid electric vehicles. We see from the figure on the left that we have 13.5% increase in the hybrid electric vehicle VMT in 2050 compared to the case of business as usual scenario, which translates to 20.8% reduction in the HEV GHG emission in 2050 in the best case compared to BAU. We see that both consumer choice in moving towards the adoption of co-optimized hybrid electric vehicle is a significant contribution to this emission reduction that we see. Using co-optimized biofuel and engine contributes significantly to emission reduction. When we analyze this for the gasoline, for the PHEVs, we see 17.7% increase in VMT in 2050 compared to BAU, with 13.7% reduction in the PHEV GHG emission in 2050 compared to BAU. But when we look at the annual GHG emission figure, the figure in the middle for the PHEV, we see that during the period of 2030 to 2045, the emission from the best case scenario is much more higher than the business as usual scenario. When we look deeper into what causes the impact, the effects that we see between this time period, we splitted the GHG emission of the best case into the emission from the conventional PHEVs and co-optimal PHEVs. And from the figure, we see that the higher emission that we see during this time period is coming from the conventional PHEVs, meaning that during this time period, the conventional PHEVs still dominate the market, with the co-optimal PHEVs taking over later after 2040, which made the emission contribution to take much more longer to reflect. Looking at the effect on the electric vehicles, we see 51.6% reduction in the VMT between the best case and the BAU case, translating to 51% reduction in the electric vehicles GHG emissions in 2050 compared to BAU. In this case, consumer choice is the major determinant factor for emission reduction, as consumers choose optimized vehicles instead of electric vehicles. When we look at the effect of the life cycle water consumption, we see that the trend that we see in the life cycle water consumption follow the same trend with the one we observe in the GHG life cycle emission. We see that the impact of introducing optimized vehicle in 2027 started to show up. The impact started to reflect after 2030 and continue to decrease until 2050, with 18% reduction in the best case scenario compared to the business as usual case. And for the mid and conservative case, we see 10% and 8.6% reduction, respectively. Looking more deeper into the driver behind the water reduction, we compare the water consumption for the BAU for different vehicle category and the best case scenario. We see that from the figure in the middle, we see that from 2030, we started to notice reduction in the water consumption for the best case scenario for each vehicle categories. And from the figure on the right, which shows the water benefit contribution by each vehicle types, we see that the 18% water reduction that we saw in the previous figure represents the benefit of 137 billion gallons of water, with major contribution from gasoline as consumers switch from gasoline to biofuel usage. We also see significant water benefit from reduced electricity consumption in electric vehicle sales as future co-optimized vehicle increases. We see that the major contribution to this emission reduction is coming from gasoline ICEV, the hybrid electric vehicles, and the electric vehicles, as consumer chooses co-optimized vehicles over the conventional counterparts and over the electric vehicles. Therefore, in conclusion, from the adopt modeling, we see that with vehicle price increase between $100 and $500, the sale of co-optimized vehicle are significant. Also, we see that there is significant reduction in environmental impact with value of 17.5% in 2050 from the best case scenario. And we also see that for the co-optimized engine and biofuel in HEVs, there is a greater contribution from this vehicle category to emission reduction compared to the impact that we see with plug-in hybrid electric vehicle. In the three cases, we see that the benefit takes long period to occur. The benefit for co-optimized conventional and co-optimized HEV started to occur after 2031, and it takes much more longer to occur in plug-in hybrid electric vehicles. We started seeing this feasible result in 2045 in PHEV. Therefore, the trend that we see in the plug-in hybrid electric vehicle deserve much more closer looks. Thank you very much for your attention.